Hello everyone. This is going to be your extra credit set of notes about harder redox reaction balancing, more specifically balancing redox reactions in acidic solutions and basic solutions. So far, we've talked about chemical reactions, we've talked about redox and what that means, we've talked about how if a substance loses electrons over the course of a reaction, it is being oxidized. If it gains electrons over the course of a reaction, it is being reduced. But we've only talked about that in neutral solution so far. But in reality, it's very rare to find a redox reaction happening in a perfectly neutral solution. And the reason for that is because quite a few substances have acidic character or basic character, even to a very slight degree. And so you're going to see some of the acidic and basic solution redox balancing happening regardless of the fact that you may not actually be dealing with a true Arrhenius acid or a true Arrhenius base. So, to balance these types of reactions, specifically in acidic or specifically in basic solutions, you're going to follow these set of 7 steps. Now, depending on which type of solution you're balancing it in, the steps are going to be slightly different, and I will walk you through that as we go. So, you are still going to be using the half reaction method just like we talked about with regular redox reactions. It's just that this time we're going to add a bunch of extra steps on top of that. So this first bit over here says that we are going to use half reactions to separate the oxidation portion of the reaction from the reducing portion first, but then we're not going to do anything else. So let's look at this reaction down here just to start out. If you forgot, let me remind you, when we approach redox reactions, the first thing that we're going to do is we're going to assign oxidation numbers to each element. So I'm just going to go through and I'm going to do that real quick. Our first compound is our PbO2. Oxygen is going to be an oxidation number of -2, and there's 2 of them. We know that this particular molecule is neutral, and so that means that our lead has to have an oxidation number of +4. Iodine comes next. That is an element, even though it is a diatomic element, so its oxidation number will be 0. Next comes our lead ion with a 2+ charge, and that is going to have an oxidation number of +2 because when it is an element with a charge or an ion, its oxidation number matches its charge. And then lastly, we've got IO3. So we've got oxygen again, which is going to be a -2. And then this particular molecule has a charge on it of -1, so that iodine is going to have an oxidation number of +5. All right. Now we want to look at the reaction as a whole to see what is happening to those elements and if anything is changing. So lead, moving from here to here, we see that its oxidation number changes from a +4 to a +2. So that thing is getting more negative. Therefore, we would say that it is reduced, whereas our iodine over here, and I'm going to draw that a little bit wonky, our iodine over there is moving from a 0 to a +5. So that thing is getting more positive, and so we would say that that iodine is being oxidized. All right. Next, we got to split those two things up into their half reactions, and then according to our set of rules on the top, we have to do nothing else yet, because again, that's what it says to do up here. So I'm just going to split those up real quick. My oxidation half reaction, which I'm going to write kind of small in the middle here, is going to be my I2 turning into my IO3 minus. For now, I am going to omit the phase symbols. I will put them back in at the end, but just for ease, I'm going to omit them for now. My reduction half reaction is going to be, again, written a little bit small and in the middle. That's going to be my PbO2, and that's going to transform itself into my Pb2+. Okay, so that is this bit up here dealt with. Awesome. Now we are going to pay attention to our first new step. And I'm going to switch colors for that. It says, after splitting the redox reaction into half reactions, follow the following set of steps. Balance elements in the equation other than oxygen and hydrogen normally by adding appropriate coefficients. If there's only one reactant, don't balance first, then just proceed to step 2. Well, there are more than one reactant, so we're just going to do number 1 normally. So I see in my equation up here that there's lead to worry about and there's iodine to worry about. There's only one lead on either side, so that's fine. However, there is a discrepancy with iodine. There's 2 of them on the left and only 1 of them on the right. So I'm going to end up adding a 2 onto the right-hand side to balance that iodine, and I'm going to move that 2 down here into my oxidation half reaction because I have done that. Okay, next we want to go and do step number 2. It says now balance the oxygen atoms by adding the appropriate number of water molecules to the opposite side of the equation. So let me show you how to do that. In our oxidation half reaction, we note that there are oxygen atoms on the right-hand side over here, but there are not any on the left. So what we're going to do is we are going to solve that problem by adding water molecules. We're doing that because, as you can tell from the phase symbols up in our molecular reaction up here, most of those things are aqueous. That means there's water around. So water is maybe not participating directly in this reaction, but it is there, so we can use that to balance some of our oxygens. Okay, we see that there's 3 oxygens on the right-hand side of this oxidation half reaction, so I am going to add 3 waters because that will add 3 oxygens on the left-hand side to balance the 3 that are on the right-hand side. In my reduction half reaction, I notice there's also an oxygen discrepancy. There's oxygen over here, but not on the right-hand side. So I'm going to add 2 water molecules on the right-hand side. Okay, so that's step 2, done. Step 3 says balance the hydrogen atoms, including those added in step 2, to balance the oxygen atoms by adding H+ ions to the opposite side of the equation. Okay, well, by adding my water molecules over on the left-hand side, I added not only oxygen, but I added another element as well. So I gotta fix those hydrogens. And based on the fact that I know that this entire reaction is happening in acidic solution, I know that there's going to be some H pluses around, because to be acidic, that means there has to be H pluses around. So I can see that there are 6 hydrogen atoms that I've added to the left-hand side, so I'm going to go ahead and I'm going to add 6 H+ ions to the right-hand side to balance that out. Okay? Moving over to my reduction half reaction, I have added 2 water molecules to the right-hand side of this thing, and so that means 4 hydrogen atoms have been added to the right-hand side, so I'm going to go ahead and add 4 H+ ions to the left-hand side to balance that out. All right, that's step 3, done. Step 4 says to add up the charges on each side and make them equal by adding enough electrons to the more positive side of that equation. So here is where the redox portion, the electron movement, is actually going to start to come in. But to do that successfully, I have to figure out what my total charge on the left and right side of each of my half reactions is. So on the left-hand side of my oxidation half reaction, I'm going to look at some charges. Water is a neutral molecule, so those waters, all 3 of them, have a charge of 0. Iodine, neutral molecule, has a charge overall of 0. So my overall charge on the left-hand side of my oxidation half reaction is 0. On the right-hand side, though, that is not the case. Each IO3 molecule has a -1 charge, and there are 2 of them. So I have 2 -1 charges based on those 2 IO3 molecules. Each of my hydrogen ions that I added has a +1 charge, and there's 6 of them. So I am going to add 6 positives onto that. -1 plus -1 plus a +6 is going to give me a +4 overall on the right-hand side of that equation. So to fix this, to fix that discrepancy between our charges on our left and right hand side, I have to add electrons to make those charge equal one another. So on the more positive side, and in this case it's the right hand side, I'm going to add 4 electrons. Because if I do that, those little negatives from the electrons I just added are going to make this overall 0 to match the left-hand side, and that's what I'm going for. On the right-hand side over here, I'm going to do the same exact thing. I'm going to count up my charges. I have 4 H pluses, so that's 4 positives. Each PbO2 molecule is 0, so that's an overall left-hand side charge of positive 4. On the right-hand side, I have my Pb2 plus, which is a positive 2 charge, and each water molecule is a 0 charge, so that's going to be an overall right-hand side charge of positive 2. There's a discrepancy again. So on my more positive side, and that's the left-hand side this time, I'm going to add 2 electrons to this side. And I'm doing that because those 2 negatives will add up to a positive 2, and then those 2 things will match. Okay, so that's going to be step 4. Done. Step 5 says that the electrons on each side must be made equal. And if they are not equal, then they must be multiplied by the appropriate integers or lowest common multiple to be made the same. So in this instance, I am doing the thing that you did already in balancing these in neutral solutions. I'm just multiplying the entire side of the equation by an integer to make sure that those electron amounts match. So looking at the 2 electron values that I've added, 4 and 2, those do not match. So to make them match, I'm going to multiply the entire right-hand side of this equation by 2. I'm just going to write that over there. The left-hand side does not need to be multiplied by anything, but just for the sake of clarity, I'm going to write in times 1, because that way our electrons will match. That's step 5. Done. Step 6 says the half reactions are then added together, and you're going to cancel out the electrons to form one balanced equation. Any common terms should also be canceled out, and the equation can now be checked to make sure that it is balanced. So we're going to do a lot of rewriting and crossing out and rewriting in step 6. So I'm going to start out by rewriting every single thing that's on the left-hand side of the arrow, both in my oxidation half reaction and in my reduction, remembering that I may or may not be multiplying by an integer to do so. So I have my 3 H2O molecules, I have my I2 molecule, and then over here I have my, 4 electrons, because remember we multiplied this entire thing by 2. I'm going to have my 8 now H plus ions and my 2 PbO2s. And if you forgot why I am putting in some coefficients, again, it's because I multiplied that entire reduction half reaction by an integer of 2. Then I can do my product side. Going back to my oxidation half reaction, I have my 2 IO3s. I have my 6 H pluses. I have my 4 electrons. And now going over here, I have my 2 Pb2 pluses and my now 4 H2Os. So that got long. All right. Now, what we're going to do is we are going to cross out things that appear on both sides, just like we do when we're writing a net ionic equation. So let's start with water. I have 3 waters on the left and 4 waters on the right, so I can cancel out some common terms and reduce that coefficient of that water on the right to a 1. I see that there are 4 electrons on the left and 4 electrons on the right, so I can cancel those out. I see that there are 8 H pluses on the left and 6 on the right, so I am going to cross out the ones on the right entirely and reduce the coefficient of the one on the left to a 2 because I am canceling out those common terms. Everything else is going to get rewritten. So I'm going to have my I2, I'm going to have my 2H plus. I'm going to have my 2PbO2, my arrow, my 2iO3 minus, my 2Pb2 plus, and my water at the end. Now, I said I was going to readdress the phase symbols, so really quickly I'm just going to go through and I'm going to assign my phase symbols using what originally showed up in my molecular equation up top. So pretty much everything except for water and except for our Pb ions are going to be aqueous, so I'll just do those two first. Our lead 2 plus was a solid, our water is going to be a liquid, and everything else is in aqueous phase. All right, so that was balancing a redox reaction in acidic solution specifically. But on the back side of your notes paper is one to do in basic solution. So let's talk about that one. Balancing a redox reaction in basic solution is going to be much the same as balancing it in acidic solution. There's just going to be one extra step that we have to go through when we get to that point, and I'll point that out when we get there. But first things first, I just want to go ahead and go through and assign my oxidation numbers to everything just like normal. So I have 4 oxygens here, and they are each a -2 oxidation number. This molecule has an overall charge of -1, which means that that manganese is +7. Each oxygen here, again, has an oxidation number of -2. The overall charge is -2, and so that means that together those 2 carbons are +6, meaning that each of them is going to be a +3. The manganese over here and oxygen over there, again, oxygen is pretty much always -2 with a couple of exceptions. That manganese is going to be a +4 to give a neutral molecule. And then finally, this carbon is going to be a +4 to yield that overall charge of -2. Now that I've done that, I'm going to go ahead and split this into my half reactions. The manganese is going to get more negative, so that's going to be reduced, whereas my carbon over here is actually getting more positive, so that one is going to be oxidized. Go ahead and rewrite my half reactions down here really quickly. I have my C2O4 2 minus yielding my CO3 2 minus on that side, and I have my MnO4 minus yielding my MnO2 on that side. Step 1 says to balance everything except for hydrogen and oxygen, so the only discrepancy that I have to deal with is this right here, my carbons being uneven, and so I put that 2 right down there. Next step is to go ahead and balance any discrepancies with my oxygens. So I see that there are 4 on the left-hand side in that C2O4 molecule, and there are 6 on the right-hand side with those 2 CO3 molecules. So I'm going to go ahead and add 2 water molecules to balance out those oxygens in my oxidation half reaction. Over here I have 4 oxygens on the left, 2 on the right. So again, I'm going to add 2 water molecules on the right-hand side to balance that out. Next step is going to be balancing those hydrogens that I just added. And so on the left-hand side here of my oxidation, I have added a total of 4 hydrogens in those 2 water molecules. So I'm going to add 4 H plus ions to that side. On my reduction half reaction, you can see that I've added 4 hydrogen atoms to the right-hand side with those 2 water molecules. So I'm going to go ahead and add my 4 H pluses to the left of that reaction. Next step is to total up my charges and then add electrons to balance out that electron discrepancy. So on the left-hand side of my oxidation half reaction, I have my neutral water molecules and my -2 C2O4 molecules with a -2 charge overall on the left. On the right-hand side, I have 2 CO3 2 minus molecules for a total of -4 for that, and then my +4 for my hydrogen ions, giving me an overall charge of 0 on the right-hand side, which means on the right-hand side, I am going to add 2 electrons to make that an overall charge of, -2, excuse me, on the right-hand side of my oxidation half reaction. In my reduction half reaction, I have my 4 positives here and my singular negative there for a total of +3 on the left. And then both of these molecules are neutral. And so that's going to be overall neutral on the right-hand side of my reduction half reaction. That means that I need to add 3 electrons to make all of that equivalent in my reduction half reaction. Next step after that is going to be to multiply each half reaction by integers to make those electrons equal one another. So my oxidation half reaction is going to need to be multiplied by 3 to give me a total of 6 electrons moving around, whereas my reduction half reaction is going to need to be multiplied by 2 to make it 6 electrons moving around. Next step is going to be to rewrite every single thing factoring in those integers into what I am rewriting. So I'm going to go ahead and I'm going to do that. All right, that took me a second. Now, here is where the extra step comes in. Because since we're doing this in basic solution, I can't have all of these acidic H pluses floating around. I have to neutralize them because there are going to be hydroxide ions around to neutralize them. So what that means is I just look for my higher amount of H pluses. In this case, it's that 12 over here. And I'm going to add an equivalent amount of hydroxide ions on either side. So on the right-hand side, I am adding 12 hydroxide ions, which is going to give me, once these things add together, a total of 12 waters. And those things will go away because they are now bonded together as water molecules. On the left-hand side, what I do to one side, I have to do to the other. So I'm also going to add 12 hydroxides. The problem on the right-hand side is that it doesn't work out perfectly. I'm going to end up with 8 water molecules and also 4 leftover hydroxides, but those things will go away as well. All right, now that I've done my extra balancing and basic solution step, I can go back and I can rewrite everything again, and then I can finally start canceling out some terms. But you have to realize that you have water in more than one spot on both sides. So don't forget that those waters will add together as well. All right, so I'm just going to go ahead and I'm going to go through and I'm going to rewrite everything. All right, now that I've done that, I'm going to go through and I'm going to start crossing some stuff out that appears on both sides. So these waters on the left-hand side will go away completely, and this coefficient of that water on the right-hand side will go ahead and reduce to a 2. My electrons will go away on both sides as well. Now that I have canceled everything out that can be canceled, I can go ahead and rewrite this again. I'm going to end up with 3C2O42 minus. That's going to be in aqueous phase. I'm going to end up with my 2MnO4 minuses, also in aqueous phase. I'm going to end up with my 4 hydroxides that I added up here. That's also going to be in aqueous phase because they're going to be dissolved in water. I'm going to end up with my 6 CO3 2 minuses. That's going to be in aqueous phase. I'm going to have my 2 waters. That's going to be in liquid phase. And then finally, my 2 MnO2s, and that's going to be in solid phase. I know it's in solid phase because the reaction up here told me that it was going to be in solid phase. So now that I've done that balancing, I just want to run a quick check just to make sure that every atom is balanced, because I already made sure my electrons were balanced with my electron canceling step, but I just want to make sure that I've done the balancing correctly. I see that there are 6 carbons on the left, 6 carbons on the right, perfect. I see that there's 2 manganeses on the left, 2 on the right, that's good. I had to count up my oxygens, but I'll do that last. I see that there are 4 total hydrogens on the left-hand side, 4 on the right-hand side, so my oxygens should work out. 3 times 4 in this molecule gives me overall 12, plus 8 more gives me 20, plus 4 more gives me 24 on that side. 6 times 3 gives me 18, plus 2 more gives me 20, plus 4 gives me 24. So every single one of those atoms is balancing out, which is what I want. My electrons from here balance out, which means that my redox is handled, and I am done. So if this was a lot for you, I don't want it to freak you out. Please recall that you will not see this on the AP test. Balancing an acidic and basic solution does not show up there. Balancing regular redoxes will, which is why that was part of your regular notes. But if you want to challenge yourself, I encourage you to give this assignment a shot. Please let me know if you have any questions.